Hi guys, welcome back to our Digital VLSA channel. Hope you are all fine. In this tutorial, I would like to discuss about n-bit triple carry adder and how to write its Verilog code. Previously, we have discussed about 4-bit triple carry adder and its Verilog code. In 4-bit triple carry adder, as we have seen, we instantiated 4 full adders, or we can use even 3 full adders and 1 half adder, because for the least significant bit we don't want any carry, so that's why we can use 1 half adder for that. Now my question is how to add 200-bit numbers. Do we need to instantiate 99 full adders and 1 half adder or 100 full adders? Is it not a pain to write that many lines? Definitely it's a pain to write that many lines. So in order to avoid, I would like to discuss about how to write Verilog code to achieve its functionality in an easier way. Now we will write design and test bench code. I opened EDA Playground. We will start with design code, module, add and sum, and inputs are a comma b. We need to declare which are inputs and which are outputs. Input, as we are discussing about n bit, so I'm providing size as n minus 1 down to 0, that is n bit, a comma b. In the same way, output, n down to 0, sum. Here I combined both cout and sum, so that's why I have written, instead of n minus 1 I wrote n. Just we will declare it as wire. It's not a problem, you can declare here also wire. And then, yeah, before writing another steps of code, first we will declare what is n. Simulator doesn't know what is n and how many bits it needs to take, because n is a variable here, so we need to declare n is a parameter here. Parameter, suppose let us assume we need to provide a value to, so let us assume it's a 4-bit triple carry adder. So for now we will try to do 4-bit only, and then in this tutorial only I will show how to add for 20 bit, or how to add for 13 bits. That's, you can keep n number of bits. And then if you want 100-bit ripple carry adder, then it is very difficult to write all the instantiations of full adder. So that's why in Verilog provides us to use for loop for the in that cases. So before using for loop, as we know in C or C++, we use I or j inside of that. For I equal to 0, I less than some value, I plus plus. In that way, I we will declare as int or something in C or C++. Here we need to declare as genvar I for I equal to 0, I less than equal to n minus 1, I equal to I plus 1. Why I didn't write here? If you write I equal to I plus plus, it won't work. Verilog doesn't support for I equal to I plus plus, because sorry, I plus plus Verilog doesn't support, whereas in SV it will support. So that's why we need to write I equal to I plus 1 for sure. Begin if, but however it is .sv file, I think it should support. Let us see by assuming that also. System Verilog is not very different from Verilog. It is the extension of Verilog. Just we will see what will happen when we put I plus plus. Yeah, first, why I am writing I equal to 0 separately means, for uh, rightmost bits, that is least significant bits, that is a0 b0, we don't have any carry input. For in full adder we know three inputs will be, that is a, p, and then carry. So but for least significant bits we don't have any carry input, so that's why we are assuming it as 0. So I am writing it in a separate block. What is the carry out of that, after adding that least significant bit c of 0, and then s of 0, a of 0, b of 0, comma 0. Yeah, this is the one. And then else, for all the remaining cases we just instantiate the full adder. C of I minus 1. Why I have written C of I minus 1 means, as we know in full adder the C in comes from the previous output of the full adder. So that's why I have written C of I minus 1. And then we didn't declare what is C. So that's why I am declaring what is C. Why? It also have size n minus 1 down to 0. C. I think that's it. If it doesn't have colon, semicolon. Yeah. And then after adding the most significant bits, it produces C of I, that is C of n minus 1, and S of n minus 1. But we didn't declare any C of n minus 1. We are assuming that it is included in S only. So that's why that C of n minus 1 we need to assign to the last bit of S, that is assign S of n equal to C of n minus 1. That's it. And with n module, after that we have written full adder here, but the simulator doesn't know what is full adder and how to add it, so we need to write full adder code. I'm writing a bit fast because we have discussed it in earlier tutorials. A XOR B XOR C is sum, carry is A B plus BC plus CA. This is carry. That's it. And with n module, yeah, sorry, A B. For full adder we have another input, that is C in. Let us assume C in. C in. Here also we need to keep C in. Here we need to keep C in. And one more place. That's it. Now we will write test bench code. Here we declared parameter the same we need to declare here also, but we will assume another thing instead of n, that is I am assuming it as size equal to, for now we will prefer 4 only, reg of size minus 1 down to 0, a comma b, wire of size 0 sum. Shit, I'm so sorry. Add and dut, these steps we discussed before, so that's why I'm not discussing here in detail. For now we will see for 5 iterations. To display outputs, I'm writing this statement here. That's it, I think. And sorry. I think that's it, our design and test bench code. Now let us see what will happen. Yeah, I'm running it. Undeclared identifier B in design.sv file, 20th line. What happened to 20th line? Yeah, here I have written capital B, that is small b, right? Again, if you press Ctrl and enter, it will run. Yeah, now it's worked fine. 4 plus 1 is 5, 9 plus 3 is 12, 13 plus 13 is 26, 5 plus 2 is 7, 1 plus 13 is 14. Now let us see for 6 bit. Here I am changing it as 6 bit. Now let us try to run. I pressed Ctrl plus enter. So it is displaying as Z. It is Z. Why? For 4 bit it worked fine, but for 6 bit it didn't work well. What's the problem here? Because we have given 6 here and 4 here. Simulator confused and it threw an error on us, right? So that's why if you declare here also 6, then it will work for sure. But as a verification engineers, we are not supposed to touch design code. Okay, only we need to write test bench code, and we need to be thorough in writing test bench code. These are some simple test bench codes. So in future we will discuss how to write test bench code in detail and in a good manner. But now these are simple test bench codes. Let us see why. If you change again in design.sv, it is working, but if you change here, it's not working. So to work well, we need to write here add in, we need to provide, this is instantiation from design, right? So here we need to write one thing, that is by keeping hash dot of, sorry, hash open braces dot, here parameter n is replaced with size. This is how we need to write. If you write this one line, we can able to see for any number of bits. We no need to change it again in design.sv file. So let us try to run here. See, it worked fine. 36 plus 1, 37. 9 plus 35, 44. 13 plus 13, 26. 1 plus 13, 14. Okay, now we will see for 20 bit. See, it worked well. You can see in calculator also by adding it. I think it should be correct. So this is about n bit triple carry adder. If you have any doubts, please let me know in the comment section so that I will definitely try to help you out. And guys, please like, share, and subscribe to our Digital VLSA channel. Thank you, guys. Bye.